The topic of today's lesson will be all about axisymmetric coordinate transformations, transforming coordinates across the coordinate plane. The last two topics we covered in this chapter was identifying points and our introduction to the Cartesian coordinate system. In identifying points, we learned all about how to determine a point that is fixed on a 2D flat plane or surface. In our second topic, we had two parts to it, two lessons, and we learned all about evaluating the Cartesian coordinate system and establishing our own. In this lesson, we will be learning about coordinate transformations or moving coordinates across the coordinate plane, more specifically reflecting them or creating symmetrical figures across axes, so the y-axis and the x-axis. Learning goals for today. Explore the process of transforming the coordinates of a graph. Grasp the relationship between the transformation of coordinates and the axisymmetry of graphs. Introduction. What is the definition of a figure that is axisymmetric to line A? A figure that is folded in half along the line A and the halves on both sides of A can completely overlap is an axisymmetric figure. So, for example, what this is saying. Okay, what this is saying is if you had a heart, this is not perfect, but say it was perfect, okay, and both sides were the same. And it had a line down the middle, and this line was called A. So, this figure, this heart shape, will be axisymmetric about line A, because if you fold it across line A, both sides can completely overlap. It is perfectly the same on both sides. So this line would be called the axis of symmetry in this figure. How do you determine the position of point P in the Cartesian coordinate system? Well, here, as you can see, we can draw a perpendicular line from point P to both the y and x axes, and then we can find that A is the x coordinate of point P, and that B is the y coordinate of point P, and then we can write it out that way. Axisymmetric coordinate transformations. Explore. Coordinate relationships between two figures that are symmetrical across a coordinate axis. In triangle ABC and triangle A1B1C1, so these two triangles plotted right here, is plotted as shown on the coordinate plane. Answer the following questions. What positional relationships do triangle ABC and triangle A1B1C1 have? Well, after reading the title of this section, you probably have noticed that it is symmetrical about the x-axis. Just like the earlier example of that heart, instead of line A, these two figures are symmetrical about the x-axis. So that means that if you fold them across the x-axis, they'll overlap perfectly. Okay, so ABC and A1B1C1, they're congruent because the areas and their side lengths are the same, right? And also, what makes this different from the heart example is that they're two separate figures. They're not one figure that is axisymmetric itself, but they're two figures that are axisymmetric across the x-axis. So these two triangles aren't connected or anything, they just are reflected across each other. Triangle ABC and triangle A1B1C1 are symmetrical across or about the x-axis. Fill in the coordinates of A and A1, B and B1, C and C1, and observe the relationships between them. So here are the coordinates for A, A1, B, B1, C, and C1. So first, think about what you notice between their different coordinates. Two distinct patterns that you might have noticed is that their x-coordinates are equivalent and that their y-coordinates are opposite. So now what caused this change? What caused this change was that they're reflected. I'm saying the word reflected a lot because that is the type of transformation that this is. And you're not going to learn that yet, but it's always good to start using mathematical language. So they're reflected or they're symmetrical about the x-axis, meaning that they have equivalent x coordinates and opposite y coordinates, which makes sense if you think about that. If point P and MN is its x and y coordinate is in triangle ABC, so it's within triangle ABC, then the coordinates of P1 that is in triangle A1, B1, C1 would be what? Well, according to the patterns we just discovered, we know that P to P1, since they're both in triangles ABC or A1, B1, C1, it means that they must be symmetrical across or about the x-axis, meaning that M would be M, but N would become negative N since the y coordinates have to be the opposite. In the Cartesian coordinate system shown on the right, there is a flag in quadrants 1 and 2. So there is a flag, a graph, the shape of a flag on both sides of the y-axis. What is the positional relationship between the two flags? Well, again, as you can see, that they are symmetrical across the y-axis. This means that if you fold them across the y-axis, they can overlap completely. Fill in the coordinates of A and A1, B and B1, C and C1, D and D1, and observe their coordinate relationships. So here are their different values. And as you can see, they have opposite x coordinates this time, yet they have equal y coordinates. So point P exists within ABC. If that's true, then the coordinates of P1 in triangle ABC, A1, B1, C1 would be what? Well, this means that P and P1 will have to be symmetrical about the y-axis. And according to the patterns right here, we know that the x-coordinates have to be the opposite, meaning that M is negative M, but N is still remaining N since the y-coordinates are the same. Due to the last two problems, what is the relationship between the coordinates of 2 points that are symmetrical across the x-axis? What is the relationship between the coordinates of 2 points that are symmetrical across the y-axis? If 2 points are symmetrical about the x-axis, the x-coordinates are the same, and the y-coordinates are the opposite. And conversely, if 2 points are symmetrical about the y-axis, the x-coordinates are the opposite, and the y-coordinates are the same. So therefore, for points that are symmetrical about the x-axis, the x-coordinates are the same. And for points that are symmetrical about the y-axis, they have the same y-coordinates. Let's do some additional practice. In the Cartesian coordinate system, the coordinates of the points P, 2, 3 reflected about the x-axis are 2. Given that A and its coordinates are A1 and A1, its coordinates are 5B, are reflected across the y-axis. So make an emphasis on that, reflected across the y-axis. What does A equal and what does B equal? I suggest you pause the video to solve these blanks on your own. And for the second problem, and the first, think about the patterns that we found earlier. Okay, the answer to the first problem would be -2, -3. Right? Because if 2 points are reflected about the x-axis, then they're okay, so this would be, the correct answer to this would be the same x coordinates. So this is actually 2 followed by -3, and the y coordinates are the opposite. And for the second problem, A would be equal to -5, and B would be equal to 1. Because if 2 points are reflected across the y-axis, they would have the same y coordinates but opposite x coordinates. Explore 2. Graph transformations caused by coordinate changes on the Cartesian coordinate system as shown. So let's first connect the following points on the Cartesian coordinate system. 0, 0, 5, 4, 3, 0, 5, 1, 5, negative 1, 3, 0, 4, negative 2, 0, 0. And what kind of pattern did you get? Well, we can create points all along here. And what pattern did you get? So connect these and then see you on the next slide. If you keep the y-coordinate of each coordinate unchanged and multiply the x-coordinate by negative 1, how will the graph change? Think about how this relates to the two distinct patterns we discovered earlier. The coordinate changes would be, so the top would be the original and the bottom would be the transformed coordinates. As you can see, the x is now its opposite value and y is the same because you multiply the x-coordinate by negative 1. So this was the original shape. If you reversed it, then it would have been another shape. And this sort of looks like, I don't know, it sort of looks like a type of kite or fish to me. The two figures are symmetrical about the y-axis. Multiply the y-coordinate of each coordinate by negative 1, and the x-coordinate remains unchanged. How will the graph change that way? The coordinate changes would be as follows. So the top would be the original, and the bottom would be the points after transformation. Therefore, the two figures are symmetrical about the x-axis. Here's our conclusion. Coordinate features of points on two graphs symmetrical about the y-axis. So xy becomes negative xy. So the y-coordinate remains unchanged, while the x-coordinate is opposite. The x values are opposite and the y values are the same. Coordinate features of points on two graphs symmetrical about the x-axis. Well, xy is turning into x negative y, because since they're symmetrical about the x-axis, x remains the same while y is now its opposite number. The y values are the opposite and the x values are the same. Discuss. What is the distance from P to negative 3? So again, this notation you've seen multiple times, but just to clarify, P to negative 3. P is the name of that point. To negative 3 would be written parentheses next to it to show that that is the coordinate of the point. So what is the distance from P to the x-axis, y-axis, and the origin? Here is P, and here is the x, y, and origin. What is the distance from the point M to the x-axis, y-axis, and the origin? So let's first do the first problem. We can first draw a perpendicular line from P to the x-axis, and that intersection point would be A, and this point here would be B. And then, after we find, the distance from A to P and from B to P, we can use the Pythagorean theorem that we learned from Unit 1 to find this diagonal distance from O to P. M is right here. M is negative 3, 4. So we can use the same thing. N and H. So we create these 2 points by drawing perpendicular lines from the point M to both the x and y axes. And then we use a Pythagorean theorem from Unit 1 to create, again, that direct diagonal. Conclusion. So 1, the distance from point P to the x-axis would be the absolute value of B, right? Because a distance can never be negative. A distance of anything has to be non-negative. So absolute value ensures that it is always non-negative. It could be 0 or positive. So that's why we have absolute signs around B. The distance from point P to the y-axis would be A is the absolute value of A, right? So A is the x-axis in this case, and we just take the absolute value of that. And for the origin to point P, the distance between the point P, AB, and the to the origin of the coordinates would be the square roots of the sum of a squared and b squared. So again, using the Pythagorean theorem. Practice. The distance from point M to the x-axis would be, well, you take the absolute value of the y-axis, of the y-coordinate, and you have 12. The distance to the y-axis would be, take the absolute value of the x-coordinate, you have 5. The distance to the origin would be 13. So Pythagorean theorem. It is given that point M has the coordinates m followed by -5. The distance from point M to the x-axis is, you take the absolute value of -5, that would be 5. If the distance from point M to the y-axis is 4, then M would be positive or -4. So again, to emphasize, in middle school and in high school, many answers to math problems will not always be one answer. Sometimes you really have to think about different circumstances. Like if one value is this, then the result would be that. And you may want to eliminate some choices. Maybe sometimes both choices would work, or even more. So that's why you always have to think clearly through all of the different solutions and circumstances. Class summary. Axisymmetric coordinate transformations. Symmetry about the coordinate axes, and graphing axisymmetric transformations. Again, the 2 skills we learned today: explore the process of transforming the coordinates of a graph, and grasp the relationship between the transformation of coordinates and the axisymmetry of graphs. Thank you so much for watching through Inquisitive Kids, and stay tuned for Unit 4, the next chapter coming up in the 8th grade Chinese math lessons series.